Convection and plate tectonics. I can relate plate tectonics to the formation of crustal features. For your starter, let's build a model to illustrate the compositional and mechanical layers of Earth, including the inner core, outer core, mantle, crust, asthenosphere, and lithosphere. So let's drag and drop these labels. So we want to start with the center of the Earth. We call that the inner core. And just above that is the outer core. This is what's going to heat the mantle. So the mantle is that orange putty-like substance inside. So as that gets heated up, it's going to rise. And that top part of the mantle is called the asthenosphere. So the asthenosphere is going to rise and then sink, rise and sink as it gets heated up again. The very top of the Earth is the crust, or the most upper part of the mantle. So here we have a model illustrating the compositional mechanical layers of Earth. Let's practice vocabulary. Pangea is the single huge continent that existed 245 million years ago. This was proposed by Alfred Wegener, the German geologist. So here's Alfred Wegener. He proposed the continental drift theory. It's a theory proposed by him in the 1900s that continents drifted apart from each other slowly over time. The theory was rejected because the mechanism that moved the continents could not be explained. So he could not explain how those continents were moving. Some of his evidence were the apparent fit of continents, fossil correlation, rock and mountain correlation, and past climate data like glacial striations, marks in the rocks. So we're still practicing with vocabulary. Plate tectonics. Plate tectonics is the theory accepted today that the lithosphere, which is the upper part of the mantle and crust, is divided into tectonic plates that move around on top of the asthenosphere. Convection is the mechanism that's going to move the lithosphere. So let's have a look at this diagram. Again, you have the inner core that's extremely hot. It's heating up the mantle. The upper part of the mantle is the asthenosphere. As that moves, it's going to drag along the lithosphere, the crust, with it. Here we see a mid-ocean ridge on a divergent boundary where plates are moving away from each other. So as this lithosphere moves away, the slab is pulled by the asthenosphere. And then as it starts to cool, it sinks and gets heated up again by the core, and it makes a circular convection motion. Like some ovens, maybe you have one at your house, is called a convection oven. Practice vocabulary. Convection currents. Convection currents are the circular motion of liquids or gases. It results from temperature differences in the asthenosphere. This causes the lithosphere, the crust, upper mantle, to be in a constant motion. So convection currents. Remember that convection currents are caused by temperature and density differences in fluids. When a fluid is heated, it becomes less dense and rises. As it cools, it becomes denser and sinks. The pattern of rising and sinking creates convection currents. This same process moves the semi-solid material in the mantle. Heat from Earth's core causes the mantle material to rise, while cooler material just below the crust sinks towards the core. Scientists believe that as convection currents move beneath Earth's crust, it drags the tectonic plates along. These plates move in different directions, resulting in geological events and features on Earth's surface.
It happens because hot rock rises, heated by the Earth's core. Near the surface, the rock spreads in two directions and goes sideways. It begins to lose heat. Eventually, the much cooler rock sinks back down. Through this spreading process, the Earth's crust is very slowly dragged apart, and it's this that ultimately causes the continents to move. Where the plates collide, the rock on the seafloor containing carbon from the dead plankton is carried deep into the Earth. As it descends, this layer of rock is heated, so the rock melts, releasing carbon dioxide. And gas is returned back into the atmosphere during an eruption. The remarkable cycle is complete.
Okay, we are going to watch another video on convection currents, and I would like that you write a sentence about what you notice, okay, during this video on convection, and what do you wonder about convection?
Take a deep breath. Get ready for one of the most hypnotic things you'll ever see in a science class. Have you heard that heat rises? Well, here, it's true for yourself. I've got some food coloring on the bottom of a plastic container, and there's a hot mug right underneath the red food coloring. As it's heated, the water rises. But I want you to look closely and notice something else. The blue on the sides is being drawn in. You can see it better when I speed it up. Here's the thing I want you to remember. When water moves from one place, it doesn't leave a void behind. Water from somewhere else has to move in to take its place. That's why you can see the blue food coloring coming in from the sides. You can see it better from above. Watch that blue food coloring get drawn in. You see it? The hot water reaches the top, and then it gets pushed toward the edges by more hot water rising from underneath it. As it goes out to the edges, it starts to get cool, and cool water sinks just as hot water rises. And if you watch really carefully, you can see it sink and get drawn back toward the middle. These are called convection currents, and you see them moving here in two big waves. They're one of the major things that drive ocean currents, especially the deep oceans. But it's not hot water rising that drives the ocean currents. It's really cold water sinking up near the poles. Here's a piece of ice that I froze with some blue food coloring in it, so you can see how cold water sinks. As water sinks at the North Pole, for example, water has to flow up from southern regions to take its place. And these currents travel around the globe, some of them taking 1,000 years to complete their course. Understanding convection currents will help you get a grip on weather systems and the movement of Earth's continents over the eons, and even the workings of a lava lamp. If you want to try this for yourself, click on this link for all the directions you'll need. Thanks for watching.
Okay, so that was pretty cool. You noticed that hot water rises, cool water sinks. This happens in our ocean. So this is a great way to model ocean currents. Maybe some things that you might wonder about, what I wonder about is if cool water is coming from our poles and warm water from our equator are rising up, what would take place during global warming? Are our convection currents in the ocean going to be affected by global warming? So some things to wonder about.
Take a deep breath.
Okay, so what I'd like you guys to do now is sketch your observation from the videos that we just saw. Be sure to show and label the following items in your sketch. So we're going to drag and drop labels and arrows to this drawing. So this is a model. This is where our heat source would be, just like it was in the video. So a hot plate under the box. So we're going to look at Earth's lithosphere and mantle. And we're going to use red arrows to show hot material in the mantle, blue areas to show cool material in the mantle, maybe Earth's core, convection cells, and arrows to show the direction of the crust. So I'm going to minimize, and here is where we can drag and drop. So what's our heat source? We are going to say it's Earth's core, right? And that core is going to heat Earth's mantle inside the crust. Our lithosphere is going to be our crust, right? I'm going to put that up top. Now I'm going to use these arrows. I'm going to drag this one over to show hot air rising. Okay, so I will use this to show my direction. Maybe I can put that over on this side. So hot air is, or the mantle's asthenosphere is rising because it's getting heated by the mantle. And then what we have is that cool material sinking to get heated back up by the mantle, right? So let me just put this over here so you can see a little bit better. So we know that cool air sinks, or we can say the cool part of the mantle is going to sink, and then it's going to get heated up by that mantle again. So what I would like you to do is really illustrate convection. So warm material rising, cool air or material sinking. And this convection is going to drag the lithosphere, the crust, apart. So that sometimes it depends on what arrows you're really using. I think maybe a better way would be to reverse that. Okay, let me drag these guys over here. And that kind of shows it better. So, looks good to me. So as we have that convection currents happening underneath our crust, it's going to drag that crust apart. Okay? So let's look at some analysis questions. The source of heat that drives convection in the mantle is the core, right? The inner and outer core. The process of convection affects the lithosphere by dragging those slabs apart, or dragging those slabs in different directions and causing motion. So convection affects the lithosphere by dragging it along. The way material moves in the mantle and movement of tectonic plates is related because, so let's think, the way material moves in the mantle and the movement of tectonic plates is related because, remember, in the mantle you have that rising and then sinking, the convection. That convection motion is going to be the mechanism, the driving force that moves plate tectonics. So let's look at a star connection question. Scientists recently discovered that rocks collected from Franklin Mountains in West Texas and rocks collected from mountains in eastern Antarctica were exactly the same age. Further research showed that the rocks were chemically and geologically the same and came from the same magma source. This discovery provides evidence of A, coastal erosion, B, plate tectonics, ocean currents, or D, glacier melting. So if we found similar rock and mountain features in West Texas that are matching up with geological rocks and formations from eastern Antarctica, what can we say that this discovery provides evidence of? Okay, plate tectonics, right? Suggesting that perhaps Texas and parts of Antarctica were once joined. That's why we're finding those similar rocks or mountain formations. So you would just type your answer there.